All right, I think we'll go ahead and get started. Thank you all for being here today, both those in person and on Zoom. It is my pleasure to introduce our speaker today. We have Professor Adrian Lozano-Duran, who heads the Aerofluids Learning and Discovery Lab, co-hosted between MIT and Caltech. And today, Adrian will be talking a bit about using machine learning for fluids. And with that, I'll go ahead and hand it over to you.
Yeah, thanks for the kind introduction, and also thank you for coming to this talk that I hope you find interesting. So my first slide is just an overview of what we do in my lab, so you can have a picture of things I'm interested in. Most of the things that we do are related to fluid dynamics and applications to space. So there is a part of the component of what we do in my lab that is related to methods, try to develop methods for cause and effect. That is something I've been very interested in my group, and also for control modeling and how to learn in general how different variables interact in complex systems. And then every time I think of a complex system, I'm thinking of a highly nonlinear and chaotic system like a fluid dynamics. Then there's another component that is more applied, not so focused on the theory and methods, that is essentially the CFD. And in this talk, I'm going to be discussing this, how we develop closure models, most of the time applied to external aerodynamics. I also have a small component related to experiments. So we do some PAV to collect data on airfoils, and this is framed to help us construct the models and gather data. Nothing very fancy, so it's a small component of what I do, but I also wanted to mention that. So today, I want to acknowledge this project. So this project is mostly funded by Boeing. There is also a component by NASA. There are many people working on the project. It's a big project. I'm showing you an overview of my students and postdocs that they worked before, or they are working actively now on the project, and also our collaborators from NASA and from Boeing. And we also have some funding from NSF that provides some support for this. And in particular, many of the results that I'm going to be showing here, or the version of the model, are related to Imran and UNON. So I wanted to make sure that was clear. So I'm showing many of the developments that they have been doing these last years. So what is the challenge that we are trying to address here? Maybe you're familiar with this. So I'm using this schematic of an aircraft as a motivation. So you can think of the flow over an aircraft, and there are many different features, or conceptually we can separate different physics. You could have a corner flow with some three-dimensionality. We can also have separation or shock waves, is transonic, or laminar to turbulent transition. The boundary layers could be very thin. You have pressure gradients. So there are many different physics. And if we want a closure model to be accurate, then we'll need to be aware of this physics, and it has to be aware of this physics, the model. But the goal is that because there are so many physics, and they are also coupled, that if you really want to actually assess the qualities of an aircraft, so a quality of an aircraft could be the lift and the drag. So the way to go right now is a flight test or a wind tunnel experiment. So there are many wind tunnel experiments, then there's a flight test, and that's really the truth. But what many people would like in industry, in aerospace, is to move in the direction of certification by analysis, that in this context mean like we have a simulation. These are very high fidelity simulations. This is still an expensive simulation. But the idea is that it's very accurate. It will give us the answer with very low error. So those predictions, they need to be very good. I'm quoting here some numbers like 1 or 3%. It really depends on the quantity, but just to get an idea. So what are the challenges in this case? So one I already mentioned is this high-dimensional, multi-regime, multi-physics. So we need to address that. Then there are complex geometries, these typically, like an aircraft that would be considered complex geometry. There are limitations in the computational cost and resources. So we are thinking here of high-fidelity simulations. So these are not cheap, fast models. It's a high-fidelity model, what we are looking for, but it still is much cheaper than an experimental campaign or an actual flight test. But we need to keep in mind that these simulations still, they need to be bounded in terms of the resources and the time. And we need to make sure that we have some uncertainty quantification and we have a workflow that is consistent and a way of generating models and versions that we can trace back and we can improve. So this is a bit what motivates what we are trying to do. So I'm showing here like the number of wind tunnel campaigns for an aircraft design. So you can see that in the 70s, the amount of time that you will spend in the wind tunnel, so you will have close to 80. So you will need to go to the wind tunnel, test a design. It doesn't work as you expect. So then you change the design, you come back and you test that again. And at that time is where CFD appeared and people in aerospace industry started to use the CFD. And that was successful in the sense that it, among any other things, other methods, so they were able to drop the amount of experiments that you need to go in the wind tunnel to 40, maybe close to 20, then 10. But then during the 90s, mid-90s, that has been stagnant. And it's a problem in a way because we will like to do this virtual design as much as we can, and you can imagine why. And there is this rule that is very heuristic, but this is what many people working in aerospace and CFD will think of, is that if you think of 1 hour of CFD, so maybe it's a few $1,000s and you can get results in one day. But if you think 1 hour of a wind tunnel could be $10,000 and you get your answer in 1 month or a few months, and the flight test would be the most expensive one. And it could take you years. So you would like to spend in the CFD as much time as you want. And ideally, this is what we like. We have a design. What we would like to do is to bring this wind tunnel campaign to 1. So we have our virtual simulation. We predict all the qualities, lift, drag, or stability moments that we need. And then we still need to go to the wind tunnel. That's going to be important. But it's just a way of making sure that everything is correct. But that's it. So we minimize the amount of wind tunnel as much as possible. And obviously, once that you build the aircraft, you want to make sure that you don't need to change anything at that point. So this is a way that it's been stagnant. So it's there. So we have 10. And there are also many reasons for this, but this is that there's a bottleneck in the closure models that we use for CFD. Most of the industry has been using runs. There are some limitations in runs. Now, industry like Boeing and Airbus, they are moving to LES. And this is going to be the framework I'm going to be discussing here, like higher fidelity simulations. So this is the project that we are working on. It's called the BFM model, is the Building Block Flow Model project. So we are trying to develop a closure model for LES that is a general purpose. So general purpose means that we are not assuming any particular case. We are not trying to fit a particular case, but it has to be general purpose in the context of aerodynamics. And typically, most of the time, external aerodynamics, although we also do some internal flows. But here I'm showing representative cases that we run with this model. Some of them are subsonic or transonic, could be the like turbofan or the typical subsonic or transonic aircraft, could be also in high lift mode when you are landing, or supersonic aircraft, or up to high speed vehicles. And there are models that you can, in the context of runs, mostly that you can tune to be good at one case, but we don't want 20 models that is each of them one at one case. We want one model that is good at all 20 cases. Because then in a way that's more reliable, that we are not overfitting a particular case. We are trying to make sure that we capture some physics that are intrinsic to the different flows that we want to capture. So this is the main idea. And what I'm going to tell you a bit, I have 3 parts. The first one is I'll go a bit more over the challenges that I described very high level, but in terms of computation and the numbers. Then part 2 is going to be describing the model, how we get the model, all the training, the architecture, how we have some explainability of the model, uncertainty quantification. And the third part is we'll show you some validation cases, some cases that we didn't train for, and we try to make predictions. So let's start with the challenge. So what is the problem of solving the aircraft? So, I mean, we know the equations that we need to solve. We need to solve conservation of energy, mass, and momentum. And that's it. I put that in a computer and I get the correct answer. And most people would agree that for this particular problem of an aircraft, that's what you need. So this, we know the physics. The problem is that if I want to put these equations in the computer and I want to solve them, I need to discretize my space. I need to create a grid. And I can count how many points I need. And the number of points that I need is related to the smallest scales in my flow and the largest scale in my flow. It's that ratio, what is going to give me what I need. So you think about, yes, where the flow is the most complicated part of the flow, that are the boundary layers over the aircraft. I'm going to need to put most of my points there. So they could be millimeters or centimeters, that might depend on the Reynolds number. And then you can have very small scale motions that again could be millimeters or even microns in some cases. That will give you across the wall a separation that could be 1,000 or 10,000, sometimes even more. But the problem is that then you need to distribute that over all the aircraft. So then when you make the numbers of a grid that you will need to resolve all the smallest motions that you have in the flow and cover all the large scale of your problem, then you get something that it could be to the 10 to the 20 or 10 to the 25 grid points. So if I'm allowed to have that grid, then I could solve my equations and it would be a reliable answer. But these numbers are very large, so typically we cannot afford that. Yes, some rough estimates, for example, if I take all the aggregated power that we have in the top 500 largest supercomputers, I take the 500 largest supercomputers and I put them all together. That I cannot, but let's imagine that I do that. So I have 15 exaflops. That's how many operations per second I can do. And I will have a memory of 35 petabytes. So that's the aggregated computing power. If you think of this problem that I'm discussing here, the number of grid points, and then you consider that you need to match your equations in time, and that will multiply also that factor, you will need of the order of 1 million exaflops. So you see, we are at 15 now. I mean, 1 million, we are not getting 1 million exaflops anytime soon. If you look at the memory, it's kind of the same story, like we need 10 to the 5 petabytes. So that's the amount of memory that to load the solution in the computer. So the problem with this is that this is not happening now, or it's not happening in 100 years, unless we completely change the paradigm. We compute things, but this is the von Neumann machine classic paradigm. So we are stuck with this. So the way to think about this is, okay, let's give up and let's not solve all the motions in the air that are very small and very complicated. So let's think in a different way. How about I have a grid that I can afford and I design that? I would like, what is the largest grid that I can put in a supercomputer, and then I can get the answer in a few days, or between 1 day or 1 week, depending on the fidelity that I want. So that will give you grids that are of the order of 500 million or 1 billion, and those are the grids we are talking about here. And they look like a lot in number of grid points, but if you compare with the estimates before, they are extremely coarse. So I'm actually throwing away many motions in the flow that I cannot resolve. So the problem of that is that those motions that I'm throwing away, they matter. They are there and they contribute to the forces, to the heat flux, that will translate into the drag and the lift of the aircraft. So the paradigm that we use for that, and is the one that I'm building the model for here, is the wall model large LD simulation. So it's called wall model because we replace the boundary conditions at the wall by another boundary conditions that they are accounting for the fact that I don't resolve all the scales. That's called a wall model. And then we also modify the equations with a correction on the right-hand side. And that's the grid scale model, accounting for these small motions that we don't have in this grid because it's very coarse. So in a way, they are doing the same. It's just in the field, traditionally, people tend to separate the models, but they are just accounting for the motions that we cannot resolve with our grid and that effect. So the way the wall model works is we'll collect some information slightly far from the boundary, and it will predict the fluxes, the heat flux and the momentum flux at the wall. And then the grid scale model will gather some information locally in the grid, and it will make predictions of the extra correction that you need to add in your right-hand side to predict some quantities of interest that you care about, typically mean velocity profiles or mean fluctuations or mean temperature. And this is not the only paradigm. This is the one that is wall model LES, but there are other versions like hybrid runs and DES. Those are also okay. It just happened to be that my interest and expertise was in LES. So, but many of the ideas here probably can be applied to any other paradigms for CFD. So what I'm highlighting here is imagine that this is my grid, and I were able to zoom in and see what the flow is doing there. So the flow might look like that. So it's actually very complicated. So these are extremely coarse grids. So this grid, if I were to look at the motions underneath the grid, could be 100,000 times smaller than the grid. So this is extremely coarse. But this is what we can afford. Yeah. So the equations that we solve, they look like Navier-Stokes. The governing equation is conservation of mass, energy, and momentum, and this is a compressible form. And then we have the boundary conditions, that is the wall fluxes and heat fluxes. And what I'm showing the equations there that maybe you are familiar with, because this is just Elias equations that look almost like Navier-Stokes, plus a correction term. And in the red boxes, I have the closure model. So I have a closure for momentum, and I have a closure for energy, and then I have a closure for the boundary conditions of 4. So we are, these are the 4 models we are developing. So we need to come up with these 4 models. So this is what the BFM is. It's the collection of these 4 models that we redesigned, and we discover them in a way all together at the same time. Okay. So let's see how the model works, and I'll probably keep it very high level. So I apologize if there are many technical details that I don't go over, but I'll try to at least convey the idea. So this is really the idea of the model. So any model is based on some assumptions about the physics. So this is the assumption I need to make: is what are the smallest scales that I cannot resolve? What are they doing in the scales that I do resolve? And that's really the model, and everything else is just implementing that idea. So this is the idea. And the name of the model comes from this. I have some simple simulations. These are affordable. And this is my training set. And this I call the building blocks. They are typically very simple, not only as the ones that I show here, but you get an idea. I'll show other examples later. It's typically a flat wall, and I can have 2 walls as a channel, or I can have 1 wall as a boundary layer. The wall could be flat. Sometimes there's some roughness. And I have a motion. In this case, the walls, they move with different velocities, and I apply different pressure gradients. And the idea is that these are very high fidelity. So I can resolve all the scales, and I can understand very well the effect of the smallest scales on the largest scales on these building blocks. And the idea is, like, if I were to zoom in a particular portion of the wing, that I'm taking here the aircraft as an example, I'm assuming that the flow that I'm not resolving is it looks like the smallest scales of these blocks. So I can infer what those scales are just by looking at these collections of small building blocks. And that's the main idea, is that these missing scales in more complex cases, they can be retrieved from the smallest scales of these simple blocks. Now, the largest scales, I don't worry so much. I mean, the largest scales, my grid is resolving the largest scale, so those are okay. The problem is the effect of the smallest scales on those larger scales, and they are coming from that. And this is the strongest assumption of the model, and it is literally what sets the bottleneck of the model. So that's there are, on top of that is kind of the building block flow assumption. There are other requirements that I'll go over them very briefly, because these are just things that you always need in a model. It has to be invariant under rotations, translations. It has to be Galilean invariant. It has to be dimensionally consistent. And these are not assumptions. These are, if you don't have these, then your model will break, or I can break it very easily. The main assumption is what I just described, so that's the main idea. There are other assumptions about the spatial locality, quasi-equilibrium, outer layer similarity. I don't go over all of them here. But these are all important. They are somehow derived from this main idea. But if you break any of those assumptions, that will translate into errors in the model. But the main approach is that, okay, now I'm going to use a neural network to retrieve the effect of those smaller scales and then account for them in the complex cases that I haven't seen. So a bit of the overview how that works. So imagine I take again the small region of the wing and I zoom in. This is how my grid looks. It's an structure because my model has to work for any complex arbitrary geometry, so I cannot assume any structure in my grid. It could be, in this case, it follows a Voronoi pattern. And I have a component of the model that is far from the wall. That's the Sagrit scale model component. It will get some invariance of the velocity gradient tensor. It will use a fit for a neural network and get some effect, the result grid. Then there are another 2 networks that are related that I have this split because some of the networks are taking care of the fluxes at the wall. Other one is taking care of the grid scale far away, and there is one in between coupling them for consistency. But the network at the wall, it will get some velocity, also invariance, and it will get some temperature, density, the typical grid size that also will go to the other neural network in the top. Another thing that the model does, it can also resolve or account for roughness that you cannot resolve. Roughness has a similar problem as trying to resolve all the scales of the motion. The roughness is so small that if you try to geometrically resolve the roughness with your grid, then most of your points are going to go there. And then suddenly you need orders of magnitude more points. So what we do is, okay, we don't have a grid that follows the roughness. This roughness, for example, could be ice, or in a high speed flow could be ablation, come from ablation. So we just provide some geometry of the roughness. So the model is aware that there is some grid scale roughness, and it will account for that when predicting the fluxes at the wall. So typically, it will predict more drag and more heat flux when you have roughness. So that information also goes into the model, just specifying some properties of the geometry, like that's what I show in this schematic. Okay, so this is kind of big picture how it works. Now, it's a bit more involved than that, because the model is divided into 4 components, but they all look like that neural network structure. But here I'm trying to give you a bit more of detail. So the way the model works, we have a baseline model. So this is a model for the grid scale model, for the wall model. It's just making predictions, and it's trained on these simple cases. Then we have an error model. So this error model is not training simple cases. It's training more complex cases for which we know the solution. And it learns errors from the baseline model. So we can have an estimation of, when we run this model, the baseline model, what are the typical errors that we get. And there are 2 types. Epistemic, meaning that our model haven't seen those physics before. Or aleatoric here means that these are physics that are unpredictable. So we don't have enough information to predict those physics. Then there is a component that is explainability in a way, and is divided into 2. There is a classifier. The classifier will tell us what the model thinks, what the model thinks are the physics that you are predicting, and I'll talk about that a bit. And there is a confidence. So the model will also give you a confidence on the predictions. And all that information we collect to what we call this expert model, and that will make the real prediction. So what the expert model would do is to get the information from the baseline model, the error model, and the confidence. If there is an error and the confidence is high, the expert model will correct the prediction. So then it's better than from the baseline model. If the confidence is low, even if there is an error, then the expert model will stick to the baseline prediction and to be safe. And even if the confidence is extremely low, almost 0, what the model would do, expert model, is to revert to an analytical form that is an equilibrium wall model, that is a traditional wall model that we have. That is what people use in industry. And the idea is that we want to avoid the model extrapolating very far from the training domain. So all these approaches to be conservative. We have 3 predictions: the traditional prediction, the baseline prediction, and the corrected prediction. And we try to pick the best all the time. Okay. So to do all these 4 modules, we need some training data. I touched on this a bit. So the training data is not only these simple channel flows. We also have some boundary layers. And what we do is to create this DNS database, a direct numerical simulation. All the scales are resolved. We use different Reynolds numbers, from low to high Reynolds number, different Mach numbers from almost incompressible to Mach 4. We have smooth walls. We have different rough walls. We also have laminar flows. We have boundary layers with different pressure gradients: adverse pressure gradient, favorable pressure gradient, 0 pressure gradient. We have cases with separation, have cases with a strong heat flux at the wall, without a strong heat flux at the wall. So this is an example of one of those simulations, how it would look like. So these are, again, simple, but very highly resolved. This is the discriminant of the velocity gradient. You can think of how the flow is rotating. And just to give you an idea that even if the cases are simple, they are still computationally expensive. So we have been generating this database for a while. So the full raw database is of the order of 700 terabytes. This is raw. That is not that we fit this to the model, but this is the raw data. So this is the data that we run, and from this we extract quantities that we care about. We have to digest this, and this is what goes to the model. And I don't talk about this much, but there is some CS component of how to read this database and train the model. If you just want to read 700 terabytes without doing anything, just read it. It could take you actually days, unless you do it well. So, and it doesn't fit anyway. So there are many hidden details there. But to be honest, a bit boring because there are no physics. It's just, but we need to make it work. And my students know about it and they suffer. So not so easy. For curiosity, I look for this. I asked, this is according to ChatGPT, how many data was used to train ChatGPT 5.5. And it told me that it has like of the order of, it doesn't tell you exactly, but this is what it will tell you, 13 trillion tokens. That is 300 terabytes. So, and I think that to train the ChatGPT, they have a budget of $1 billion. And I don't have $1 billion. I can guarantee you that. But also I have to say that this is like post-process, like the digested 300 terabytes. So when we digest our database, we can shrink it to a few terabytes. So that's okay. But the raw one, we need to deal with that somehow. Okay. Another part that is important of how we train the model, and I don't go over that a lot, is that we have all these building blocks and we need to get all these grid scale models and wall models, and they need to be compatible. And these grids are very coarse. They need to be compatible with the solver and they need to be compatible with the numerics. So the way we train this is with reinforcement learning. We set up many cases. We march them at the same time, integrate forward the equations. There is a model that is common to all of them. We are updating the agent, that is the model, so it performs well at all the cases for predicting mean quantities, mean fluxes at the wall, mean velocity profile, and mean temperature. And we do that for a bunch of cases, but not all of them fit in memory. So once that we train a model that works for a set of cases, we send another batch of cases, we train for them at the same time, and we do what people call in the jargon of ML, like memory replay. From time to time, we don't want the model to forget what it learned. So we replay samples from the other cases from time to time, and we force the model to still be good at the previous cases. But this is expensive in a way, because still these are cases with million grid points that we need to run and march for, and we need to do it. So this is a GPU intensive. It takes weeks, and we use maybe 100 GPUs to train the model. So it takes a bit. It's not like a laptop training. And also there are many tricks that we change the exact way we do this, because we are learning how is the best way. I don't know if this is the best way. This is the one that is reasonable and seems to work for us. But we have been changing this approach back and forth. But this is what we do essentially: reinforcement learning, training, integrating forward, and matching the statistics, and training the model to be good at many cases at the same time without forgetting previous cases. What we do. Okay. So let me show you a few examples of a baseline model. So the model was already trained at this point, and now these are cases that are not used for, some of them are used for training, others are not. And I'll show the distinction later. So these we collect from the literature. Some cases are from our own database. So here we have 73 cases, would be of the total 1 million samples. So 1 million samples are defined here. Like if you look at a given point at the wall, that would be one sample, and you look locally in that direction. But just to show you that there are different geometries, but it's still simple, like it's still like a periodic hill, airfoil. And the reason is because we want to test the model in something that is slightly more difficult than building blocks, but also we know the solution for. I mean, I don't know the skin friction in the aircraft as a function of space, so that we don't know. So this is a preliminary step. So this is showing what overview what the model does. I'll explain this what it means. So the vertical axis is the error, is the average error per case. So each case will have thousands of samples, and it will be a bit difficult to visualize that. So from those 73 cases, they are all here, and it's an average. Each case will have like 100,000 samples. The vertical is the error from the current model, and the horizontal axis is the classical standard model. So what we do is we go to the people from Boeing and we ask them, what is the model? What is your best practice? Give me your best practice. The model that you use, the best grid scale model that you use, the best how you tune it, and they give us that model, and that's the error that we report here. So it's a bit misleading the pro because there are a lot of points focused there. I'll talk about that, but this is what we are trying to do with this model. We are trying to make sure that at least in most cases we are pushing the solution in the right direction. And that would be underneath the dashed line. Dashed line means same error as the best practice. So below that is we are improving with respect to that. And this is why we have different regions. So this is the region of improvement. So this is what we care about. And if you count how many cases are here, so in the red region, the top corner, the one that we don't improve, that is like close to 8% of the cases. So there are 8% of the cases where we don't do better than what the best practice would do. And well, that's how it is. And then what we do is to try to learn about those cases and why that's happened. So it's useful in a way. But I want to mention here that most cases that you see here, we didn't train for. I mean, these are the cases we train for, they are okay. I mean, if they are not okay, we train the model again. I mean, we know the solution and we are aiming to predict those well. So those are very well predicted typically. The challenge is the ones that we haven't seen before. So the model have never seen any of these red cases. Okay. So this is what the baseline model does. And this, I just wanted to highlight this, that each case is not 1 point. Each case is one case here. One is, for example, a full airfoil. So the full airfoil will have the solution as a function of the core of the airfoil at different locations. So we test the error of our model compared to the error of a equilibrium wall model that is the best practice. And then we can have some standard deviation and we can break down these errors closely. But for here, I just giving you an overview. Okay. So the next step is the error model. So this is the way of thinking in a way. So I trained my model in these very simple cases. And now I test these other cases that you just saw. And the model is doing well sometimes, but sometimes it's not doing well. Sometimes it's not doing well because, well, there are physics that I didn't have before. So because I have that data and I have the answer, why not correct for that? I mean, why throw away that data? If I know the answer and I can use it for training, let's train an expert model that is going to take care of that. So that's what the error model is doing, is trying to learn all those cases, not all of them, because we still keep some of them like hidden to test, but it's trying to get better at predicting things. But so in the end, we are going to be using all the data we have. But what is useful of this is that it's giving us a feeling of what the errors that we can expect. It's giving us a feeling of the expected errors. And as I mentioned before, well, I'll go over the error model a bit later, but okay. So the other component is this I'm breaking down a bit what we are trying to do. So the way we think about these errors are lack of physics. And that was epistemic, is that we didn't have a knowledge. So maybe my training data for the baseline model, there is a regime, a Mach number, Reynolds number that has never seen before. And the way the heat flux at the wall scales in a different way, and then it doesn't know that, and then it will just break down there. But I can technically correct for those. I can learn those. Other are aleatoric, and aleatoric here means that unpredictable. So these are, I know that my model is not doing well, but I cannot fix it. I cannot fix it because in a very simple way, given an input, I have multiple outputs. So I don't know which one I should choose, and there is no way out. The only way of solving this aleatoric error would be I need my model to gather more information about the flow. I will need to increase the stencil of the model. That will increase the complexity. So for now, those I give up. What my model would do is give an average of the different options that it has, and I live with that. But I know when that's happening. I can actually report that and say, okay, my model, this region of the aircraft in this corner, there is high aleatoric error. It means that my model cannot distinguish which building block has to use. It's ambiguous. And then there is the confidence that we are trying to also build into the model. And it has these two components. One is the model can also tell us what physics are used when making predictions. And the other one is how confident is in that prediction. And you can think of the confidence asking the model, have you seen this before? So the way this is done is a standard way it's a generalization of a Gaussian process. So this is a very nice way of splitting between epistemic and aleatoric, but it's based on a spectral normalized neural network. So this is a bit with more detail what I just told you. So we are trying to answer this question, what error comes from the lack of physics and what error comes from the unpredictable cases. And this error model has two data sets. The same data set that I used to train the baseline model, data set one, but also this other complex database that can learn errors from, and all that fits into that, and it will be able to predict these epistemic and aleatoric errors. And the other component that is done all at the same time, so this is the same SNGP, what is also telling us the model is what physics are used for prediction. What this means is that when the model is giving me a prediction, I can actually go back and see what training data was used to fit that part of the neural network. And I can put a label in that data that I understand. For example, an adverse pressure gradient boundary layer. So then my model can give me a prediction. I can tell me this prediction comes from the fact that I learned predicting adverse pressure gradient boundary layers. So this is what I'm using. And this is useful because then I can actually check if it makes sense physically or not. And I'll show a few examples. And also that's related with the confidence that in a naive way you can think of how far I am from my training data. So I can measure how much my neural network is extrapolating. If I am within my training data and I don't have any aleatoric errors, then I can give you a high confidence because the model has seen that before. And it will just tell you, like, I know what is this. I've seen this before, and this is the prediction. However, if there is some high aleatoric error, the confidence will drop. The model will say, like, I have seen this before, but I don't know which case I have to pick to make the prediction because they are incompatible in the training data. Or it's just extrapolating. It's like, I've never seen this before. I'm so far from my training data. And that confidence will drop. And this is an example of, just to illustrate this with in a way that is more concrete. We run the model now in this case that we don't have such a detailed information in space and time. And this is the HIRM, the CRM high lift is an aircraft in a high lift configuration. Here I'm showing you some results just to show you the CP at different locations. And we have a reference solution that is the best practice from Boeing. For this grid, we use the same grid as the people from Boeing. The blue is our prediction, just to show that it's always pushing the solution, and it happened in this case in the right direction, even if not perfect. But the point I wanted to highlight here is the part of the explainability. I'll come back to this case later. But this would be an example of what the model is telling us about the predictions. So the picture on the left is the physics used for predictions. And I have different labels that I created myself because I understand what they mean. So it's for a human to interpret things. So there is a blue region that means adverse pressure gradient. So this is a high angle of attack aircraft. So what will happen is that you have the leading edge, then the flow will accelerate very fast. That has to be red. That makes sense. So it's a favorable pressure gradient. Then you will have a adverse pressure gradient. The flow will decelerate. And that's what you get in the blue region. And then the colors are not the best, but you can also have separation. And this is the purple at the very end of the trailing edge, telling us that the flow is separating there. And the idea is that, okay, I can look at this and think that, okay, it makes sense within the knowledge that I have. What I would be very concerned is that if the blue region is, for example, red, meaning that the flow is accelerating. I mean, the flow is not accelerating over the wind, and we know that this is very basic. So I want to make sure that the model is doing the right predictions for the right reasons. And we use these maps to run across many cases. And every time that we identify regions that they make no sense, and we go there and try to understand why this doesn't make sense. And the model is making this prediction. And when we revise the model. So this is also helpful for us as a path to improve the model. And maybe for a practitioner, it's useful just to sanity check to look at and say, okay, it seems to be meaningful. Then the one on the right is the confidence. So from 0 to 1, typically close to 1 means that the flow is pretty, the model is pretty confident that it has seen that before. Now, that doesn't mean there are no errors. You might have high confidence and the errors might be large, because confident here means that the model it's able to find a building block that locally looks like what the flow is doing there. But you can break some of the assumptions and that will give you errors. But at least in this case, everything is okay. And we use the confidence for grid refinement. We choose which regions of the flow we should refine. Usually when you refine the grid, the confidence tends to go up. If the grid is very, very coarse, it means that you don't have points to resolve even the boundary layer. So there is no magic. So if you have 1 point across your boundary layer, the confidence is always 0 essentially. So this means you need to refine. And if we refine and the confidence doesn't go up, it typically means that we are missing physics. So we can also use that to try to understand what physics we are missing. Okay, well, this is the same, but we can get this map as a function of the surface or any region in space. So it's just a bit overwhelming, that solution, but this map is a function of space and time everywhere. So, but just the other view. Okay, so now how everything comes together for the expert model. I want to show you a bit about that. So the expert model is collecting all this information and putting it together. And what I'm showing here, this plot is very similar to what I was showing before, but now I'm not comparing with the best practice, traditional practice. I'm comparing with my baseline model. So I have the expert model error in the vertical axis and the baseline model. So anything that is below the dashed line is an improvement with respect to the baseline model that typically was already an improvement with respect to the traditional model. And again, I do this, I have some cases that are trained for, some cases that are not trained for. But what we are trying to make sure is that we are always pushing the solution to the right direction. And this is what we are getting here. And this is every point here against a full case. I'm showing you one particular case. This would be an airfoil, and this is the friction coefficient. And I'm showing you experiments from the truth. Then the other case is the green, is EQWM, is the equilibrium world model. It will give you that line that tends to be off. And then the baseline model was doing a better job than the traditional model, but still in the laminar part didn't work very well. So if you think this airfoil, there is a laminar part close to the leading edge, and then it will become turbulent. And then the expert model is improving on that. And this is a way also of not throwing away the data that we have. There are still cases that we don't predict, and we cannot correct for them. And the reason for those cases is just that we don't have, our input is not complex enough, so we cannot tell them apart. There are high aleatoric errors. So, but in general, the train is okay. Okay, so this is an overview of the model, and I just wanted to show maybe a few cases, and also wanted to show you how we develop the model. So the model is not like fixed. Typically, we generate versions. So we have our training data, we implement the model, then we test it in simple cases, then we test it in more complex cases. We generate all these modules. We make sure that everything makes sense or learn about the problems. And maybe we include new physics, new training data, and we iterate again. And we go through this cycle, we generate a new version like 1.1, 1.2, 1.3. And I didn't talk about this much, that this model is implemented in GPU, and the solver that we use is Charles, that is from Cadence. And the reason for that is because that's the solver that people from Boeing uses. So we create a module that we give to them, and they test it internally, that they don't share with us the results. But they give us feedback about some cases that are open geometries that we could use to reproduce some problems, if any. And many of the results I'm going to be showing next is version 1.5, and now we are finalizing the version 2 that maybe will take, I don't know, half a year to get done. And this is also about the computational cost. So we try to put some effort in making sure that we don't get a lot of overhead because of the neural network. So traditional models are very simple to evaluate, typically, because they don't involve a very large array of matrices multiplying each other. So what I'm showing here is that we try to do some optimization to make sure that there is some overhead, but it's not a lot. So this I'm showing this normalized time of running the solver. Imagine that I run my solver on that aircraft, and I use two traditional models. That's the blue and the red. So the blue is the Breman's grid scale model, and for the world equilibrium world model. The red is the dynamic Smagoinski model and equilibrium world model. And the green is our model, version 1.5. And I normalize everything with the Breman model because it's the cheapest, so it's 1. So you can see here that our model lies in between. It's not as cheap as the Breman model, but it's actually cheaper than DSM with equilibrium world model, so it's competitive. And I think that we want to make sure that we are not only reducing the errors and the predictions, but we are doing it at a competitive cost. So making sure that we are increasing the cost of maybe 10% with respect to Breman. So that's okay, because then when you look at the accuracy, we are improving generally across many cases by a lot. So that's fine. Okay. So we have tested the model in many cases. Some of them are simple, others are like a pipe, bumps, aircraft of different types, high-speed flows or turbine blades. I listed here over 300 untrained validation cases. That is true, but to be honest, most of them are simple, more closer to the channel or the pipe. This is a challenge of the model, is that we don't have data for complex cases as massive as we would like. I would like to have the data for, 1,000 aircraft and just test the model across 1,000 aircraft to see that this is not a coincidence whether I'm doing well or not in that case, or very complex geometries, thousands or 10,000 cases. But those are coming from experiments most of the time, so it's not easy. And I don't do them myself, so I cannot even complain. I'm grateful already that other people got those results and are able to share that with us and with everyone. So this is an example. I just want to go over a few. One is, yes, our model BFM, and I'm comparing with those two classical models, Breman, equilibrium model, and DSM. This is a prediction of the mean profile in the pipe, just to show you that things look okay. We improve that. This is another case. It's a Gaussian bump. It's a case that people see every day like a lot because it's a smooth body separation and is very sensitive to the details of the model. And here I'm giving you an idea of how the flow looks, and then the pressure and friction coefficient that they measure in the experiment. And just to show again that the idea is like we are trying to improve with respect to looking at traditional models. So in this case, the experiments are the dots. So the blue one is our model, and it tends to follow those dots more closely. This is also the mean velocity profile that is more clear. So this is also experimental data. And then you see that what happened with at this particular grid that is very coarse, what happened with the classical models is that they completely miss the separation. But we were able to capture that because our model is trained for very coarse grids. It's accounting for the fact that the grid could be very coarse, but traditional models cannot do that. But for us, it's important because I could resolve this bump with a lot of points, but if I translate into the aircraft, it wouldn't translate well. If I take the same portion of the aircraft similar to this bump and just put, in this case, 500 million points, then the aircraft, that's going to translate to 10 billion. So I cannot do that. So that's why we intentionally pick these grids that are the grids that we are thinking always of the full application like an aircraft. This is another example of the explainability. So you see the confidence. So usually the model is pretty confident, not everywhere. So there is a part that related to the separation that you can see behind the bump where the confidence drops. And we look into this, what happens is that the flow there is very three-dimensional. And the model actually has never been trained with three-dimensional flows in the sense of the mean flow three-dimensionality. I mean, turbulence is three-dimensional, but if you look at the mean flow, most of the cases we have, they are 2D. So there are some vortices in the corner and the model hasn't seen that before and the confidence drop a lot. Although it seems that they are not affecting a lot the predictions, but we know now that for the next version of the model, if we want to capture that, we need to have some mean flow three-dimensionality or in our training data. And the other one is the flow classification. Again, we are trying to see that everything makes sense. The flow decelerates before the bump, then accelerates, then decelerates, then there is a purple region that is separation, and then it will go back to zero pressure gradient. So it's not like there is ground truth about this, but we just use this as a sanity check that we don't see anything very weird. This is revisiting this case again. I just wanted to show you the lift coefficient, the polar for different angles of attack, and I'm using the same color code as before. The blue is our model, and the triangle and square are the traditional models, and we compare with experiments. So in this case, we were able to predict pretty well lift and drag, or at least improve, even if it's not perfect. Although the moments we were not able to, and this is also a case we try to understand why, and the moments they are very sensitive to the way the forces are distributed over the wing. So this seems to imply that we are not doing a good job at predicting the CP, the pressure coefficient, in some regions in the wing. And actually, when I was showing this case before, I showed different cuts of the CP, and you could see that there was some deficiency. Still, we tend to improve with respect to the models. And again, this is what we're trying to do here, to make sure that we improve with respect to the traditional model and we learn the deficiency so then we can correct for it. I have also a few examples of high-speed flows. For example, this is a challenging one. This is a compression ramp, Mach 8. So there is a shock wave at the leading edge, and also there is roughness at the wall. So, and this is coming from an experiment from Prince. And here what we try to predict is the heat flux at the wall. because that's the only quantity we have to from the experiment. So the experiment is the red dots, and then our model would be the blue line. And in this case, I don't compare with any other model because there is no counterpart model that will be able to do this. So there is no model that can work. There's no closure model on LES that can work at high speed flows for the Sagritte scale model and for the heat flux and accounting for roughness at the same time. I could put the equilibrium well model. It would be way off. And I used to do that and people complain, so I remove it. So, okay, there is no LES counterpart, although there are correlations that people use. These are not, they don't solve Navier-Stokes, but they have correlations for this, and those work okay, but they are also very tuned. This is another case. This is a nice video of one case for what we did for, this is the MSL capsule. And this is not, we don't have the data for this, but this is what people from NASA do. They have this hemisphere. This is also challenging. So this is high Mach, and there is also roughness. And in this, we have different variations of the roughness and different cases of different Reynolds number, Mach numbers. And again, here the challenge is to predict the heat flux. That's what matters the most. Skin friction is not so important in these cases, but we compare with experiments. These are coming from NASA, Hollies, and the blue is the current model. And here what I did, because I cannot compare with other closure model for LES, what I can do is to switch off my model and just to show that the model is doing something. So if I switch off the model, then essentially the flow doesn't even transition, it remains laminar, and then you get that dots, like no model. So at least I can compare with that. Okay, this is a case that we did for fun. So we did this, where we took the part of the model related to high speed flow. So I can just retrain my model without that data. And then I can run this. I can run any of the cases before, but this was more fun. I ran this X-wing and Mach 20, and then we compute the flow and the heat flux, and I try to plot the confidence of the model. And this is regions where the model is below 10%. But I just wanted to show that I can break the model. So if my model doesn't see high speed data, and then I give my model this high speed flow, then it would make predictions always, but the confidence has to drop like very low. I say 10% here, but actually I should replot this. It's even below 1%. So this is very bad. So in a way, this is a warning that we can have built it into the model to tell us something very wrong is happening here, or you shouldn't use the model in this case. And this is obvious, but sometimes it's not so obvious. In the bump, at the edge of the bump, there are these 3D vortices, and the confidence dropped almost to below 20%. So I wasn't knowing that was going to happen or not, but now I know, and now I can look at it, and now I can say, what is the training data that I need to capture that? So in a way. Okay. So this is essentially everything I wanted to tell you. And I always like to discuss a few limitations. There are actually many. The main one I already mentioned this is there is these assumptions to build a model. Most of them are related to this building block assumption and some locality and quasi-stationarity. And if those break, then that will translate into errors into the model. I think that's live. There is no way of solving that. But what we are trying to do is to be able to detect those cases. So the model can break, and because I know the model well, I can build cases in which the model will fail, but at least it will tell me back, I think I'm not doing a good job here. So then look at it. Another question is this database of fundamental building blocks. I just told you I have these boundary layers and these channel flows, but why is that the best case? I don't know. Maybe there is a very smart way of building a high fidelity database that it would perform much better. Then it's very expensive to generate a database because it's coming from DNS. And if you ask me what is the database that you would like to, I would like to cover all my dimensionless space. And I will need like 100 million GPU hours. That is insane amount of time. And I don't have that. So we are trying to think if there are other ways of gathering data, maybe through experiments that they are very high quality and I can get many of them. I can have an automated experiment where a robot will change many cases for me and working 24/7 and get me back the data. Well, there are many fixes we don't account for, reacting flows, three-dimensionality, multi-phase flows. There are different separation patterns we don't capture and it will fail. The bamboo is an example. And then the confidence could be high, but still the model might fail. And we have seen that, like you have a false positive or false negative. And we need more validation data in complex cases. That not so sure how to fix it, but I would like to have many complex cases that are very well documented, they measure many things. So then I can go and evaluate the model there. Those I wouldn't use for training probably because I don't want to overfit those cases maybe, but still it would be very useful to inform what I need to change in my training data. And there are a bunch of publications, everything in my website that says building block flow model is one of these components. So they are not in one paper, they are all scattered because we have been working on this for a while, but you can just go there or just, if you want to discuss, send me an email. I can point you to the right paper to look at whatever component you are interested in. So I think that's it. I'm happy to take any questions.
Thank you so much for that wonderful talk. We'll start with questions in the room, and then if there are any questions over Zoom, if you should just please put it in the chat, and we'll ask it out here to Adrian. All right, so question, Mike?
So, great talk, thank you. But something I'm looking at is scaling laws or these types of surrogate, or not surrogate models, closure models, right? Or general AI enabled closure surrogate models for fluid mechanics. I'm wondering if you've looked at like generating some sort of preliminary scaling law for a foundational end-to-end model for something like flow over an entire airframe, or is that something that like still in the works?
Yeah, that's a very important component. I mentioned that one of the requirements is that the model has to be dimensionally consistent. That means that your model has to be formulated in dimensionless form. And if you apply Buckingham Pi theorem, there is an infinite number of ways of doing that. And we have a method to find the best possible dimensionless numbers. And we have some work called dimensionless learning based on information. So from all the possible dimensionless groups that we can form with our input variables, we find the one that is the most predictive. And that's something that we do a priori before training any neural network. You can do that. We have a method for that. We find the most predictive dimensionless numbers. You can think of those as your scaling laws. So those are the quantities that they really control the quantity that you want to predict. And then once that we have those, we train a neural network using those as input and output. And sometimes I explain that here. I might even have a backup that is exactly this, discovering the most predictive input and output. But sometimes it takes a lot of time to talk about this, but this is the main idea. We maximize the information that the dimensionless input has about the dimensionless output. If you maximize that, that is something that you can do regardless of the function that you are going to use to model your problem. You can show that will minimize the error of the model that you get later. So it's essentially based on that. There are other methods for doing that, but this is the one that we like. And it's very important. If you don't do that, then the performance might drop a lot because we need to make your model doesn't need to fit the data, has to find how the solution scales with the dimensionless numbers that control the problem. And that's the key. And that's how the model can actually extrapolate a lot in dimensional space. But in dimensionless space, everything is very contained all the time. That's why the confidence in the aircraft was very high. You can say, how is that possible if the range loss number that you have there is much higher? Well, because I can rearrange my inputs and outputs in a dimensionless form that it will bring all together to the same order of magnitude. Yeah, that's related to that. Yeah, maybe I can go over that if that's of interest. So this is the main idea. So the point of this is that you don't need any model. So I don't need to use any model. So this is, you can prove the following. You can prove that how much you can predict about an output is related to the mutual information between that output and your input. And if you think about this, is regardless of the model. It doesn't matter what the model is because what models are doing are always the same. The model is taking the input and extracting the output from your input. They don't have anything else. So if your input is meaningless, doesn't matter what model you use, you can predict nothing. So there is no model in between. This is applicable, this limit, you just need to, the only thing you need to do is estimate the mutant information, but you don't need a model for that. I don't need to specify in this notation that I have here. I have this yellow region is the information in my output. The blue region is the information in my input. And what matters is the overlap. And I try to find the dimensionless form that will increase that overlap. And then I'll build a model. The model is that F model. But that F model is independent of that overlap. What I need to do is to find the dimensionless coordinates that they maximize that overlap. And well, if you do that, you can prove that that's going to be the minimum possible error you can get, regardless of any model. And then later I can find, and this it doesn't matter if F is a neural network, a polynomial, linear regression, an analytical equation doesn't matter because you cannot get something that is not already in your input. So that's the main idea here. So I don't know, maybe it's a bit confusing at the beginning, like it's not obvious, but does it make sense? You can theoretically derive that. So, I mean, if I tell you, if I give you the number of the driving license of everybody in Washington and I tell you to predict the weather, can you, if you use a very complicated transformer with CNNs, like it doesn't matter because there is no information about the weather in the driving license number of the people. So it's predictability zero. So now think of the opposite case. If my output is exactly a quantity derived from my input, then predictability will be 100%. Now you need to find a model that is able to do that, but that is a posteriori.
Good. Just a quick clarification before I ask my question. So my understanding there is you're learning the closure term, and then you apply that. So you'll do an LES simulation, and you'll just call the closure term this ML. So this is where you get maybe modest speed up compared to the classical method. So the first question is, like, in design because you see a lot of machine learning surrogates, and they go for the full simulation. They kind of advertise 1,000 times speed. They seem you've chosen to go to.
Yeah, I think that is very different approach because I'm not trying to build a surrogate model of anything. My model has never seen an aircraft before. There is no aircraft in my training data, but I use my model to predict an aircraft, to predict a turbine blade, to predict an entry capsule, to predict a rotorcraft, an airfoil. So it's not a surrogate of anything. It's trying to do a general purpose. So in a way, it's very different. That's why I'm relying on LES equations because I want to enforce conservation of energy, mass, and momentum because I know that's very useful. And I just try to model the correcting term. That's different from creating a surrogate model for an aircraft. That is also very useful, but I would say it's a different problem. I can have simulations of 10,000 aircraft. I can run LES. I can run my model for 10,000 aircraft, and you can train an autoencoder kind of architecture that will predict, given the geometry and the flow conditions, it will predict the lift, and it will do it in 1 second. And that's okay, but and it could be used for design or for real-time prediction. But now if I give that model a rotorcraft, it's going to fail completely because why should it work? But that's not what I'm trying to do. I'm not competing with fast. I don't want fast. I want accurate. And my competition are experiments in the wind tunnel that they take months and they are very expensive. So if my simulation takes weeks using a supercomputer, it's still much cheaper order of magnitude compared to an experiment. So that's why I'm aiming at the high-end fidelity of the simulation. You are thinking maybe more of the low end could be used for prototyping, a parametric sweep for design. So it's also very useful, but I think it's a different philosophy. And that's why in that case, maybe it makes no sense to solve Navier-Stokes-like equation. It's more, it's a very clever fit to your data that you parameterize very well for small variations of your geometry, and it's extremely fast. You can even make it real time, and it's useful for things that you need fast. I
kind of agree that you get generalization if you focus very locally because you kind of hit them. The technical question on it seemed that your MLPs were evaluated in points, and then you kind of have this SNGP, spectrally normalized gaps of person. But my inspiration tells me that you want to look around the neighborhood.
That's a good point. So they are not exactly point-wise because they are based on gradients. And when you compute the gradient, you need to look at your points around. So let's say, but it's still, you are right, it's a very small stencil. So I'm just looking at one point and the neighbors, and that's it. And the reason for that is just practical because the model does not assume anything about the geometry, if you think about that. So I don't know if there is a corner or there is a wall, or I don't know exactly where are my neighbors. So if I want to increase the stencil, then suddenly I need to take into account many, if this, then do this other thing. So it's a bit more tricky to do, but I think it might be useful to increase the stencil a bit. And for that, we need to use a graph neural network. And we have been looking into that, but things technically become a bit overwhelming. So my approach was, how much can I do with this? I mean, before jumping to doing something more difficult, why don't I try to see what is the best I can do using this local stencil? And once that I can convince myself that that's the bottleneck, that increasing the stencil is what is going to make the model better, and there is no other way, then I can justify doing the graph neural network and go through all that pain that is not trivial, and preparing the training data and taking into account all the edge cases, and maybe your neighbor is not even in your same process. So, I mean, this is a parallel code. So you're looking for a neighbor, it's not even close to you. You need to find it and send information. So then technically things become a bit more tricky. But if that's what we need to do to improve the model, then we'll do it, yeah.
Instead, we have to show you one
I would be very interested in that, yeah.
Great. So we'll just take this last question from Zoom. We're 10 minutes past the hour, and then we'll call it. But Phil asks here, could you talk a little more about how you develop an error model for the epistemic and aleatoric error terms? It would seem that regardless of type, you have to have an idea of what you don't know, and could possibly be contributing to the error.
Yeah, let's go back to that. So I apologize that I don't really have a lot of details about this. So I'll try to build on this. So the idea is that first we train our baseline model in some set of cases that tend to be very simple. That's what I'm calling here training database 1. And the baseline model is trained on those cases. Okay. Now what we do is to take the baseline model and we run many cases that they are not in the training database. And that's the training database 1 plus 2. So we put all them together. Even in the one, sometimes you might get some errors that might happen. But we have a new database. It's a database of errors. And we train a model to predict those errors. So now we have a baseline model that makes predictions in cases that it wasn't trained on. And then we have an error model that tries to predict the errors of the baseline model. And it learns the scaling of those errors with the dimensionless numbers that control the problem. And now we can apply that to other problems that they were not here. And the last component is, now the question, what is epistemic? Epistemic essentially means that we had a gap in the training data for the baseline model. There is a gap. There is no data there. But by running more cases, suddenly we fill the data there. And we didn't have the knowledge, but now we do. And that's an epistemic error. And that's very easy to correct for. Then the other one is aleatoric. I can run my baseline model across many cases. And sometimes the error is not because I didn't know that region of the input space. Is because given an input, I have many outputs. And there is no solution to that. Is that if given an input, I have 10 different outputs to choose from, which one should I choose? So I don't know. I can compute the mean value, but that's an aleatoric error because I can compute the mean value, but plus the standard deviation around the other cases that I'm not picking to predict. And those errors we cannot correct for. So those we actually just live with them. But we are aware of them and we try to understand why we get them. And the last part is the confidence. And this is just trying to measure if we are close to our training data. It's a distance. You can think of a distance, how far I am from my training data. If I am within the cloud of points of my training data, high confidence. And if I'm very far away, I'm extrapolating a lot, low confidence. The other thing that can trigger low confidence is aleatoric error. that will also trigger a low confidence. So confidence is mostly distance. Yeah, I hope this clarifies, but yeah, maybe I should prepare a backup for this, explaining the steps more carefully. Yeah.
Well, unfortunately, we are 12 minutes past the hour here, so we're going to have to call it. But if you have any other questions, Adrian will be around today, or perhaps you can reach out via email. So with that, thank you again so much.
Yeah, thanks a lot.